let's go ahead and get started. Take your homework out, if you would, please. Your book's open to page 533. And you did several different problems on this page. You did 1 through 9, the odd. You did 10 through 13. And you did 18 through 20. So let's go ahead and take a look at that page 533. Quickly turning in your pre-algebra books to page 533, where your homework was. All right, there's 1 through 9 odd, there's the 10 through 13, and the 18 through 20. Thanks, sir. And good. All right, number 1. What was the missing hypotenuse, Lana?
Wait, number 1?
Uh-huh.
C equals 26.
26. Number 3, what was the missing hypotenuse, Joshua? 20. Number 5, what was the missing leg, Lana?
8 equals the square root of 7,321.
Ah, you treated it like you were finding the hypotenuse, not the leg. Joshua?
12.
Ooh, all right, let's take a look at this real quick. We've got in number 5, we've got a, I drew it backwards again. I'm forever drawing things backwards. All right, we had a hypotenuse of 61. That's your C. We've got a leg we could call B, that's 60, and we're finding a leg which maybe we could call A. So as we plug this into C squared equals A squared plus B squared, we're going to need to start with the 61 squared equals A squared plus 60 squared. Now I think we can do 60 squared in our head. What would that be?
3,600.
Right, 3,600 plus A squared equals, and what is 61 squared? We might use a calculator for that. 3,721?
Is it 11?
It is 11.
I was looking at the wrong question.
Yeah. So 3,721. Lana, remember, you don't add 3,600 to both sides. You subtract 3,600 from both sides. That gives you 121 equals A squared. And as Josh just said, that means that A equals
11.
Technically, we would say positive and negative 11 most of the time. But not in this case, just 11 our
I
answer.
didn't add.
You said you had 7,000 something.
I added those two together instead of subtracting.
Right, that's what I said. You should have subtracted them instead of adding them. All right, let's see, back to number 7 for redemption. Now, Lana, number 7 didn't work out evenly. You can't actually take the square root. So when you find C, you're going to have to leave it irrational.
Square root of 85?
Right, the square root of 85. And normally we would try to reduce this down, but 4, 9, 16, 25, 36, 49, none of those go in. So there's our answer, the square root of 85. And for number 9, Joshua, it also did not come out evenly, but you could reduce that one. What did you get before you reduced, though, on number 9?
The square root of 90.
Right, so for, you would call that side C, because again, it was the hypotenuse, and you would get the square root of 90, but I assume you reduced it down to?
3 times the square root of 10.
There we go, and there's our answer, 3 times the square root of 10 for number 9. Lana, other than number 5, where you forgot to add, or forgot to subtract and add it instead, were you good to go on 1, 3, 7, 9? And Joshua, good to go on all of them? Mm-hmm. Excellent. Let's take a look at number 10 now, and you're supposed to find the ratio of similitude first, then use that to find the length of the indicated side. Joshua, on number 10, what is the ratio of similitude?
9.
I'm not asking for the answer, I'm asking for the ratio of similitude.
8 over 6.
8 to 6, right? Or we could reduce that down to say
4 to 3.
Right, so we would say the ratio of similitude is 4 to 3. And then the first triangle has a hypotenuse, it appears, of 12. And we're finding the hypotenuse of the other, and you will find the x to be 9, our answer on number 10. Number 11, Lana, what's the ratio of similitude?
4 to 10.
Which could reduce down to
2 to 5.
2 to 5. Again, I like to reduce ratios. In fact, normally we would. So 2 to 5, our ratio of similitude. And then we know in the first triangle we have a side of 6. We're finding a side in the other, and you found it to be? 15. Good to go on 10 and 11. Practicing with similar triangles. Number 12 looks like a right triangle. Is it a right triangle? Lana?
Yes.
Yes. When you say 10 squared equals 6 squared plus 8 squared, that is a true statement. It is not a lie. It is a right triangle. Joshua, number 13, looks like a right triangle. Is it a right triangle?
No.
No, it's not. It's really close though, right? You end up with 20 squared, which is 400, not quite equal to 394. So it's really close, but not quite. So no right triangle there on 13 questions on those two. And then dropping down to the bottom, numbers 18 through 20, just some more practice. Adding radicals, reducing them, getting them similar if you can. And number 18, Alana, could you add those?
No.
No, you couldn't simplify them at all, so you definitely can't add them because they're not similar. So what you see is your answer. Number 19, Joshua, were you able to simplify those radicals?
Yes.
Yes, you were able to simplify the first radical to make it 3 times the square root of 7, and then the second radical you simplified to
5 times the square root of 7.
So are they similar?
Yes.
Yes, they are. We can add 3 squared of 7 plus 5 squared of 7 to get
8 squared of 7.
8 times the square root of 7. Great job. Number 20, Lana, what did you simplify the first radical down to?
3 times the square root of 2.
Okay, but then there was already a 3 out there, right? So 3 times the 3 square root of 2 should have given us 9 times the square root of 2. What about the next radical? What did it simplify down to?
6 times the square root of 2.
Good, 6 times the square root of 2. So when we have the 9 times the square root of 2 and the 6 square root of 2, which yes, they are similar, we would get what for our answer, Lana?
15 times the square root of 2.
15 times the square root of 2. Questions on 18, 19, or 20? Yes, sir.
On number 20, how is there another 3?
Okay, so on number 20, if you look at the problem, it says 3 times the square root of 18. That's 3 times the square root of 9 times 2, which is 3 times 3 times the square root of 2. This 3 doesn't leave. This 3 comes from the 9. I think you just lost the 3 that was there all along, so if you got 3 squared root of 2, don't forget there was a 3 all along that has to be multiplied by the new 3 you just got.
That's what I did.
Yeah, I could tell. All right, questions on that. Just be careful, right, to make sure we don't lose the old coefficient that's there. Like, we want to reduce the radical, but the coefficient has to stick around for the ride.
Is that answer 15 times the square root?
Yes, 15 times the square root of 2 should have been our answer then. All right, questions on that? All right, so as we look at Pythagorean Theorem and using it, you understand there's right triangles really all around us. We see all the time. And if that's the case, then we can use right triangles to solve various problems. For instance, every time you lean a ladder up against a wall, you're making a right triangle, assuming that the house or the wall is perpendicular to the ground, which it usually is. It's a right or correct angle for building. Ramps, for instance, right? You've got a higher level, you have a lower level. You take a ramp to get up to the higher level, well, that makes a right triangle. You look at telephone poles or perhaps a lot of cell phone antennas. And there's those wires that come down, right, that hold it into the ground. They're called guy wires. And those make right angles. Again, assuming the pole is straight up and down perpendicular to the ground. Those make triangles. So there's right triangles all over the place. Let's look today at some practical problems that we could solve using the Pythagorean Theorem. Flip back to page 530, and we'll use the example I mentioned first of that ladder being leaned up against the house. Go and read the example problem for us there on page 530. Lana?
Derek needs to repair the gutters above his air conditioning unit. His ladder is 13 feet long, but because of the location of the air conditioning unit, he must place the base of the ladder 5 feet from the wall. How far up the wall will his ladder reach?
All right, so you have a 13-foot ladder. Theoretically, you could reach 13 feet up the wall with it, right? Or could you? Think about it. Do you really want to lean a ladder straight up against a wall and then climb up? Why not?
It'll fall backward.
It'll fall backward, right? Because it's front load. Okay, so you already know you need to stick the base of the ladder out a little bit to make that right triangle. Well, he not only has to stick it out a little bit, he has to actually clear his air conditioning unit. Y'all know what we're talking about, the little box outside with the fan that spins? Okay, so he's got to be able to clear that as well. So he's realized he's got to stick the base of the ladder at least 5 feet out. The ladder, though, is still 13 feet. So you see the picture there. There's the house, okay? And air conditioning unit sitting here, he's got to go out 5 feet. The ladder is 13 feet, and the question is, how high up the wall will his 13-foot ladder reach? And obviously, again, it's not going to be 13 feet anymore. Well, you realize if we kind of just put the ground in right here, there's a leg, there's a leg, there's the right angle, 13 feet, my ladder class becomes the hypotenuse, right? 5 feet would be the leg, this would be a leg. So we could say that 13 squared equals 5 squared plus whatever that height is squared. I'm going to say h squared for height in this case. So 13 squared, have we memorized that? Yeah, Joshua has 169. We've used it a bunch. 5 squared, of course. 25. And Lana, what do I do with the 25? I don't want it with the h squared, so I want to get rid of it. How do I get rid of the 25? No, Joshua. There we go. She got it. Subtract it away, right? And the reason I call on you again, subtract it, not add it, right? From the homework. So that'll give us that the height squared that we're able to reach is, what do we get when we subtract here? All right, and then again, like all pure quadratics, we're going to take that square root at the end. That's pretty easy. We end up getting what height for the ladder to reach?
12. 12.
And we'll use the same unit that was used here. We'll say 12 feet. Make sense? And that's the solution that they have.
They put positive and negative.
Well, technically positive, negative when you take a square root, right? But notice they lost the whole negative thing because notice it says only the positive answers needed. They're not trying to go down into the ground 12 feet. They're trying to go up 12 feet. So positive 12 feet. Flip back, if you would, to page 527 now. And you see a little diagram of a ramp, which again would be an example of a right triangle. Page 527. Now that particular ramp actually leads right up to the edge of the concrete, which wouldn't get you anywhere. But I want you to picture, like, for instance, a handicapped ramp. Have y'all seen these before? Okay. So on the side of the road, for instance, there's usually a curb. Well, if you wanted to make a ramp for someone, now oftentimes they'll inset them, but let's suppose we put a ramp out here into the street. Usually the curb is about 6 inches high. Well, let's suppose the ramp is a 3-foot long ramp, so 3 feet. Now, do you notice a little problem already? We're getting our units mixed up a little bit here. Hold on. We're getting our units a little bit mixed up here. So we wouldn't want to use inches for one length and feet for the other, correct? So let's change our 3 feet to say 36 inches. Now, obviously, as Glenn already pointed out, that's going to make this thing stick out into the road, isn't it? Which potentially is a problem depending on where the traffic lines are. My question is, how far into the road would a 3-foot long ramp jut out if it's going a height of 6 inches? Well, guess what we have right here? A little right triangle. At your seats, use the Pythagorean Theorem to find this length. And I'm going to go and get you calculators that you can use here. Make your life a little easier once again. How far out into the road is that 3-foot ramp going to jut out? And hopefully you realize you're finding the leg, not the hypotenuse, right? So hopefully you squared the values and subtracted the 36 or the 6 squared from both sides. Does the square root of 1,260 come out evenly? It does?
Yeah. It does.
What does it come to?
36.
No, it does not.
I did that. It was on my calculator.
All right,
I got 30.
Oh
Lana.
wait, no, that's the 1296.
1,296, which should be 36 squared, correct?
Oh, yeah.
Minus the 36. Did you ever subtract the 36
Yeah,
away?
I did.
Take the square root of 1,260 again. Yeah, that's it. It doesn't come out evenly.
Oh.
It's irrational. It can't be 36 because the square of 36 is this. The square root of this would be 36. So the square root of this can't be. It does come out irrational. Now, Lana, approximately, what is that value? The value on your calculator?
35.5.
35 point what?
5.
Well,
It's
what's the number?
49.
Yeah.
0.49 blah, blah, blah. Okay, so
5.
approximately 35.5 inches. 35.49 blah, blah, blah. Keeps on going. About 35.5 inches. By the way, notice, that's almost the full 36-inch ramp length, isn't it? Which is why, by the way, if you were to look at the front of the ramp as it's going up, usually the ramp would be rounded on the edges. So that way cars could easily drive over if it jutted out in the road too much, which usually that would be too much. Also, that's why they would often inset the ramp into the sidewalk itself, again, with kind of gradual edges in. But let's get the exact value here. Let's go ahead and reduce this down. Let's factor this down. What square do you reckon might be in 1,260?
4, yeah.
Let's get something bigger than
Well,
4. 4 is awfully small.
16.
Try it. Try it on the calculator. Can 16 go in? 1,260 divided by 16?
No.
No.
It doesn't, okay. But I'm looking at the sum of the digits and I see something.
9.
9.
Oh.
Now think about it. You said a 4 went in and I'm saying a 9 goes in. Well, if 4 and 9 both go in, what other number must go in? If 4 is a factor and 9 is a factor, if 4 and 9, then 36
Oh.
has to be a factor as well. So since we already saw the 4 and I'm seeing the 9, let's factor into 36 times something. 36 times,
No, 4 is
35.
35. There we go. Just divide by 36 on the calculator. And so when we reduce this down, what would our reduced answer be, class?
6 times the square root of 35.
It's 6 times the square root of 35 inches. So this is our approximate answer. This is the number that, frankly, the engineers are interested in. Approximately how far out does it stick? That's what they want to know. But if we're looking for the really mathy-looking answer, we can say 6 times the square root of 35. Let's look at a couple more problems together now. Turn over to page 532. Page 532. And take a look at the word problem number 23. Go ahead and read this if you would, Joshua.
Lacey's church is adding a wheelchair ramp to the sidewalk leading up to the front doors. The ramp will extend 10 feet from the door. It must also go up 10 inches to be level with the top of the steps. How long will the ramp be in inches?
Now this is a really long ramp. It is going a little bit higher to be fair, but it's a really, really long ramp. And the idea is the more gradual the angle, right, the lower the angle, the easier it is to get the wheelchair up. Lana, I don't know if you remember, but you remember Pastor Amsbaugh? Are you old enough to remember
Yeah, I
him?
remember.
Okay, so you remember then before Pastor Rands came. You remember Pastor Rands? Pastor Rands, while he was here, he tore up all the sidewalk, had all the sidewalks torn up and relaid. Well, outside Hodges Hall, the ramp that we have now was there before. And right now, we've got a ramp something like this that gets you to this level. Well, the ramp used to start right as right at where the front of that kitchen door goes, and the ramp was like that. It was frankly dangerous for old ladies with their walkers to go down there because it was just such a steep ramp. So we recognized, they said, let's tear it all up, let's put new concrete that's more gradual. So that's what they're doing here, though you might argue it's a little extreme. They're only going up 10 inches, and they make a 10-foot long, no, excuse me, not a 10-foot long ramp. The ramp sticks out 10 feet from the door. So here's the picture. I want you to draw it. Go and have a piece of paper out. We're having a 10-inch rise. This gets you level with the door. And the ramp is going to stick out 10 feet. The question is, how long is the actual ramp going to have to be?
Don't you change that to 120?
Oh, yeah.
Right, and we're gonna have to, like the last example I gave you, change this to 120 inches. So am I finding a leg or am I finding the hypotenuse?
Hypotenuse.
At your seats, go ahead and find it. What I want you to do is give me an approximate answer, because it's not gonna come out evenly, but then let's also go ahead and get the reduced answer. So get your approximate answer on the calculator, but then let's also reduce it down and get the reduced radical answer. Hey Glenn, why don't you study your vocab words? You got that big quiz coming up next week. Put the Legos away this time. Shh. I want to focus. Unless you're already done, of course, then. It's as reduced as it gets. I don't see any other squares in 145. Yeah. Wow, that's kind of weird. All right. And what's the approximate value of C? The value the calculator gives you?
120.4.
And I thought I had that here. 120.4 inches approximately. So this is your plain English answer, and then this is your mathy looking answer.
Yeah.
Wait, so,
Yeah, I saw 100 immediately because it ends in double zero, and then I looked at the 145, like it's got to factor more, but nope, 4, which means 16 and 36 can't go in. 9, nope, which means 81 can't go in. 25, of course not, because it doesn't end in 25, 50, 75, or double zero. 49, I thought might be my ace in the hole. Nope, that didn't work. And then, like I say, 81's already bigger than half, so that's it. No other roots. Questions on this? Questions on this? All right. Number 24. Go ahead and read that for us if you would, Lana.
oh my. Is that Johanna or Joanna?
I'd say,
Joe.
I don't know, Joanna, Johanna, Johanna, however you want to pronounce it. Johanna. That's a cool name. Let's go with Johanna. Why not?
Johanna biked up a steep hill segment. A map showed the horizontal distance to be 48 meters. Because of the incline, the actual distance Johanna biked was 50 meters. How high was the hill segment Johanna biked?
Hey, if you just picked your own thing, I wouldn't have had to give you Johanna, so don't be mad at my Johanna here. All right, so Johanna is going up this hill, and it's a really steep hill. And from point A to point B, Johanna travels 50 meters?
40.
Yeah, why
50
is it
meters.
50 meters. Yeah.
But, because she's not in the US, Johanna, it's a German name. In Germany, everything's in metric. The map says she actually went 48 meters. Because the map, or GPS, can only track from point A to point B from above, like the way the satellite uses it. So we have to use point A and point B here. Really, point A is here and point B is up the hill. The question is, how high up did she go as she was biking those 50 meters on this steep incline? At your seats, use the Pythagorean Theorem to find it. It's okay, you have a calculator because of big numbers, so that we don't need to whine about them, because we have a calculator. Do you have a library book out you need to return? So there's no conviction whatsoever.
I don't know.
Do you need to go to the library and ask the librarian if maybe there's a book still out? Okay. When Glenn gets back, I'll send both of you because he's probably in the same mode. my calculator because I don't know 48 squared off the top of my head either.
2,300.
Show off. I'm just kidding.
Nah, it's not clear.
Hey, that works out evenly.
Yeah.
I know that one.
Wait, please don't tell me the answer yet. I'm not done.
What's taking so long?
It does.
Because I had to get my pencil out.
It took you that long to get your pencil? We're giving the answer. What's the answer, Josh?
14.
14 meters. She goes 14 meters up in the air, while she goes 48 meters forward. All right, that doesn't actually sound like that steep of an incline, but whatever.
No.
Questions on number 24. Now that your pencil's out, you'll be able to keep up with us on this next one. Number 25. Read it for us, Josh.
A zip line begins at the top of a 20-foot tower and ends at a landing 300 feet from the base of the tower along level ground. How many feet long is the zip line?
Have you guys ever done the zip line over the Chattahoochee?
I
No.
wanted to, like,
I
my
do not
sister
want to
told
do
me
that.
how
I
much
have.
it costs, but I haven't.
Yeah, I've never done it. When I was younger, I actually enjoyed doing zip lines, and now that I'm old, I don't trust anything anymore.
Not that.
And so I'm like, I don't know, I've got this bad feeling about this, so I don't do zip lines, but it does kind of look cool. So we've got the big tower, you know, where you start on the ramp and you get on the zip line and down, 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 over here somewhere. So we know that from up here, we're going to have a certain height down, but we're going to wind up at a point. Now, in this case, it's going to be on the ground. Obviously, across the Chattahoochee, you're going from one tower to another lower tower. But it tells us that this other spot is 300 feet away from the base of the tower. So we all understand. So here's the base of the tower to this other spot on the ground where the zip line ends, 300 feet. And it tells us that the tower is how high, class? 20 feet. Do you see how drawing a picture makes the problem doable? Without a picture, you probably don't figure this. But with the picture, pretty easy, class. We're going to use the Pythagorean Theorem to find the hypotenuse. At your seats.
I'll just draw real quickly. That's why it takes me longer.
Oh, well, I already drew it, so you can just solve it. Ideally, you're drawing while I'm drawing is kind of the thought. Hold on. You need to visit the library real quick?
Oh, yeah.
Let me send you that first, and then Hayden, you can, when you come back.
Go.
That was the question. All right. All right, and 90,400. For sake of time, let's go ahead and see if we were on the right track. Did you square the 20 and the 300 to get 490,000 or 90,400? Take the square root. On the calculator, comes out irrationally 300.66, about 302/3 feet.
I got
I'm so
300.7.
confused.
Well, if you rounded at 300.7, what's the problem, Lana?
Yeah.
You're supposed to subtract.
We're finding the hypotenuse, Lana. We're finding how far you actually zip
I'm
line.
not thinking about that.
That's the hypotenuse.
I'm so stupid. I subtracted them.
Right, but when we're finding the hypotenuse, don't plug in for the c, plug in for the bases, and then the math tells us to add. So what you have to do first, and this is what I actually asked when I first drew the picture, is, okay, so class, what are we finding? The hypotenuse. Now Josh answered, I probably should have let you answer as well, but the hypotenuse is what we're finding. It's so important to identify that so we plug the numbers in the right spots. So it should have worked out this way. I ended up reducing the radical, of course, once again, the double zero ending told me I knew there's 100, and then the 904 ended in 04, so I knew there was also a 4 in that. So I got 226 times 4 times 100, which came out to 20 times the square root of 226 feet. Questions on it now? Lonnie, you understand what you should have done? Do you understand from the picture why it's the hypotenuse we're finding? Josh, questions. Were you on the right track?
That was huge.
It was. Were you on the right track, though?
I think I was.
I'll just write down the answer because I'm not going to work.
Okay, you can go back and rework it later, perhaps. I want you to do number 26 on your own. Draw the picture, figure it out. Number 26 you're going to do on your own. Draw the picture, figure out what you're solving for. Is it a leg? If so, you're going to wind up subtracting. Or is it the hypotenuse? In which case, you're going to wind up adding. So you do 26 now on your own. Reading comprehension meets math class. So if you don't comprehend, you're not going to draw the right picture.
How do you know where the numbers go?
Well, draw the picture first. Do try to keep working, Scott. I know you're just overwhelmed by my artistry, but
Wow.
try to keep working. Spelled out there is computers. I'm in such awe. I can't work. No, that wasn't what you were saying. Okay, sorry. This situation. Sorry, Scott. All right, check your picture. It said the bed of the truck, that's right here, was 50 inches above the ground. So right here is a height of 50 inches. Did we get that? And it says the ramp is, you're gonna have to look at the actual problem in the book. The ramp is 130 inches. Thank you, guys. Okay. Now, that's the ramp. That's this slanty line. And the question is, you can't back the truck all the way up against the building or there's no room for the ramp, right? The question is, how much room do you need for the ramp? So, leg or hypotenuse? What am I solving for?
Leg.
Leg. Because the hypotenuse is the 130.
Why is the hypotenuse?
Because it's the longest side.
Because the ramp is the slant, right? The ground is straight and level, and then measuring height is always straight up from level. So the 50 inches height is a leg, and the distance behind the truck is a leg as well. The ramp is that slanted 130 inches. That's my hypotenuse. I'm finding this missing leg. check your work. Should plug in 130 squared for the c squared, 50 squared for either of the legs. I wouldn't call the other leg x squared, okay? And when I squared and subtracted, I wound up with 14,400. I'm like, wait, that's 144 times 100. Both of these are rational. 12 times 10 gives us me a nice, easy, rational 120. Or you could take the square root of the calculator and get 120 inches that way. But he needs to leave at least 120 inches. See, how many feet is that?
160.
120 inches. How many feet is that? 10 feet. 12 inches in every foot. There's 120 inches. That's 10 feet. We need to leave 10 feet of room behind the truck to put the ramp down. Technically, plus a little bit of room to maneuver the cart behind the ramp, but the ramp itself is going to need 10 feet behind the truck, is our answer. Or you could leave 120 inches for your answer. That would be fine as well. But usually we think in terms of feet when we're measuring. You're going to practice a couple of these for homework this evening. Practicing with figuring out how to set up the drawing. It works your brain deeper than just plugging into a formula like we did in 7th grade. Now let's put some thought into how to set up the picture. This time, if you would, go ahead and turn over to page 534. And your homework included last night reading over some of this content from pages 534 and 535. Begin a section on trigonometry. Now, some would argue that Pythagorean Theorem is in part trigonometry as well, because trigonometry simply is the study of triangles, specifically, most commonly, right triangles. And you understand that in a right triangle, there's always one particular side that's the biggest. Class, that would be the hypotenuse. Okay, good. I was waiting for both of you to answer. Wanted to hear both of you. All right, head off hand there, Lana. This is stuff you know, so calm down and just focus. Hypotenuse is the longest side. Now, there's a reason the hypotenuse is always the longest side. Because in any right triangle, remember, in fact, in any triangle, the three angles have to add up to 180 degrees. The right angle is, of course, always 90 of those degrees, which means the other two angles between them will add up to 90 more, correct? It could be 10 and 80, could be 30 and 60, could be 45 and 45. I'm just going to make up the numbers 20 degrees and 70 degrees, for instance. But they have to add up to 90, which means they're always smaller than 90 each, right? Because this is the biggest angle, this is the biggest side. You'll discover that the second biggest angle has across from it the second biggest side. And the smallest angle will always have across from it the smallest side. So if I were to draw some random triangle, not even a right triangle now, and I said that this is my littlest angle, this is my bigger angle, and this is my biggest angle. I'm going to call this side L, this side J, and this side S. Which is my biggest side, class? S, because it's across from the biggest angle. Which is my smallest side? J. No, J, because it's across from the smallest angle. And of course, the medium-sized side would have to be L, because it's across from the medium-sized angle. What if I drew a triangle here, and I said that this is my tiny side, and these sides kind of look equal, but let's say this is my middle-sized side, and this is my biggest side, and I call the angles X, Y, and Z. Which angle would have to be the biggest angle? Angle Z, because it's across from the biggest side. Which would be the smallest angle, class?
Y.
X, because it's across from the smallest side. Of course, Y would be the medium-sized angle because it's across from the medium-sized side. Do we see how there's always going to be that relationship, though? Big angles have across from them big sides, and little angles have across from them little sides. That's a relationship that is true in any triangle. Now, the book points out, though, that specifically, let's just say in a right triangle, if you were to draw a right triangle and you kept one angle consistent, the ratio of the sides would stay consistent. Look at the sketch there on page 534 with the little green triangle. You'll notice that for a 30-degree angle, if the opposite side is, say, an inch, the hypotenuse is always 2 inches. But if you were to stretch it out, blue triangle now, make the opposite side 2 inches, the hypotenuse doubles as well to 4 inches. If you were to then stretch it out some more and double the hypotenuse again, or the opposite side to 4 inches, now the hypotenuse would also double and become 8 inches. So that the ratio is always the same. Do we see that? There's some consistency here. Now, we're looking at the ratio specifically there of the opposite side and the hypotenuse. But there's actually 3 major ratios in trigonometry. And the best way that I can help you remember is the way that I learned these. And it's with an old Native American saying. We used to say Indian saying, but that's not politically correct anymore. So a Native American saying, Sokatoa. Now, the Indians understood this, that trigonometry is easy. Sokatoa. That's what it means in Native American. I think it was specifically Cherokee. Actually, I lied. I made all that up. This actually is representing 3 different trigonometric ratios. They're called sine, cosine, and tangent. Now, in any right triangle, let's go ahead and just put this guy up here. In any right triangle, there are, of course, as I said, 2 acute angles. Lana, do you want the top acute angle or the bottom acute angle? Pick one. Top. Okay. So Lana said we're going to mark this top acute angle up here. Now you realize with respect to this angle, there is one side across from it. We call this the opposite leg. Because of course, it'll always be a leg that's across from an acute angle. We would of course call this side, class, it's always called the hypotenuse. And then we have this other leg. Now this leg is certainly not opposite the angle. It's actually part of the angle. It helps to make the angle, doesn't it? It's up against the angle. So we're going to call this the adjacent leg. Adjacent simply means next to. So your next door neighbor lives in the adjacent house to you. We're kind of spread out because of COVID protocol here, but if you were sitting in the seat next to each other, you would be sitting in adjacent seats. Adjacent just means next to, and this leg is up against the angle that Lana picked. Now, if Lana had picked the bottom angle, well now, this is not adjacent to this angle. Rather, class, with respect to this angle, we would call this the opposite leg. And now this would be the adjacent leg. But this would always be the hypotenuse, wouldn't it? Sokatoa is simply a way to remember the 3 trigonometric ratios. The sine of any angle is equal to the length of the opposite leg divided by the length of the hypotenuse. Regardless of what those lengths may be, you make a ratio or a comparison of those 2 lengths, that gives you what we call the sine of that particular acute angle. The ka stands for this, that cosine is equal to the length of the adjacent leg over the hypotenuse. You notice they're very similar, leg over hypotenuse, but for the sine it's the opposite leg. And for the cosine, it's the adjacent leg. So, ka, toa. What do you suppose toa stands for? Lana?
Tangent equals opposite over adjacent.
Good. Opposite leg over adjacent leg. And you're right, Lana. Typically, I'll drop the word leg because I'm lazy. But for this first time, I wanted to go and write that up there. So let's suppose I had a right triangle. And we're going to go with Lana's angle. I'm going to call this triangle angle C for the right angle, which by the way makes this side C. I'm going to call this angle A, which by the way makes this side A. I'm going to call this B, which makes this side B, the opposite. All right, so if I wanted to find the sine of angle A, or the cosine of angle A, or the tangent of angle A. Notice the abbreviations, sin, cos, tan, okay, because we're lazy, we only use 3 letters. Drop the E, drop the ein, and drop the gent. All right, so sin, cos, tan is how we abbreviate. This stands for sine of angle A, cosine of angle A, or tangent of angle A. Let's suppose I knew that this side here was, let's just say 10 units. Let's suppose this side was 6 units and this side was 8 units. You actually see that little pink triangle there in your textbook there, though I've got it standing up instead of laying flat. Well, let's look at the angle A. Sine is a ratio of the opposite leg's length to the hypotenuse length. What is the length of the opposite leg to angle A, class? 6. What's the length of the hypotenuse? 10. So it's a ratio of 6 to 10, or we could reduce it and say 3 to 5. For the cosine class is what over what? Adjacent leg over hypotenuse. Well, what's the length of the adjacent leg to angle A? 8. What's the length of the hypotenuse? 10. So the cosine's a ratio of 8 to 10, or we could reduce it to 4 to 5. And for the tangent of angle A, class, tangent is the ratio of opposite leg to adjacent leg. What's the opposite leg again? 6. What's the adjacent?
8.
So the tangent of angle A must be
3 to 4.
6 to 8, or Vaughn is ahead of me, 3 to 4, reducing it down. Good. Do we see how easy it is to identify sine, cosine, and tangent? Look, if you would, at the purple triangle now. Look at the purple triangle. And let's again look at angle A in the purple triangle. I'm going to put it on the chalkboard as well. But it says that we've got a leg here of 7, a leg here of 24, and a hypotenuse of 25. And we're looking at this angle A. Well, if I wanted to find the sine, well, actually, I'm going to be really lazy here. If I want to find the sine of angle A, I would need to first identify, class, what is the opposite leg. Well, what is the opposite leg?
24.
24 is opposite or across from A. And the hypotenuse pretty clearly, class, is 25. And that doesn't reduce, that's the ratio, that's the sine of angle A. If I wanted the cosine of angle A, class, I would need to find the adjacent over the hypotenuse. What's the adjacent to A? 7. Now, I've had students say, well, isn't the 25 adjacent? No, that's the hypotenuse. Adjacent means adjacent leg. 7 is the leg that is adjacent. The hypotenuse is adjacent to both angles. So the 7 over the hypotenuse, class, which again is still 25, and that doesn't reduce. And then for the tangent, class, that's going to be, tangent, class, is going to be
opposite leg over adjacent.
There we go, opposite leg over adjacent leg. Or in the picture, class, it's going to be, what's the opposite?
24.
Over the adjacent?
7.
7. See how easy it is? You just find what's the opposite, what's the adjacent. Look at the next page. There's a blue triangle here. And we've got our angle is this time angle B. That's okay. And we've got our opposite is 5. The adjacent is 12. And the hypotenuse, 13. So if I wanted to find the sine, cosine, and tangent of angle B, Lana, what would be the sine of angle B?
5 over 13.
Good. 5 opposite over 13. So, ka, toa. All right, so Joshua, what would be the cosine, ka, of angle B?
12 over 13.
Good. Adjacent over hypotenuse. 12 over 13. And Lana, what would be the tangent, toa, of angle B?
5 over 12.
5 over 12. And there's my SOHCAHTOA, my sine, cosine, tangent. Again, the way I memorize these is I just remember these letters. SOHCAHTOA. And as long as you can spell it correctly, you'll remember that sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. Now for homework tonight, you're going to try some of these. Just do your best. You didn't get a chance to practice in class. I was hoping we would have time. We didn't have time. Okay, so do your best on the homework, and if it's not great, we'll fix it tomorrow. Your homework for this evening is to do page 533, numbers 16 and 17. Page 533, numbers 16 and 17. Now those are those word problems where you're going to draw pictures. You just have 2 of those. Then on pages 538 to 539, 538 to 539. I want you to do homework 1 through 8. Homework 1 through 8. Listen carefully. On 1 through 6, they only ask you to find the sine of one of the angles. I want you to find the sine, cosine, and tangent of whatever angle they name. Does that make sense? So we're going to do a little bit more than what the book says to give you practice with all 3 trig ratios. So it'll say to find the sine of this angle, go ahead and also find the cosine and also find the tangent in each case. We'll take a look at that tomorrow. All right, have a wonderful rest of your day. You are dismissed.